Welcome to our course on calculus. We have been discussing about the continuous functions in the previous lectures, and in this lecture too we are going to continue with the examples of continuous functions. Let us get into it. The problem that we are going to see first is f of x is defined in the form of x square if x is a member of irrationals, and is defined in the form of x when x is a member of rationals. So this is the function that is given to us. Hopefully you have watched the previous lecture, so that I am assuming that you know what was the concept that we have seen in the previous lectures, and I am directly going to this problem. If at some point this function is being continuous in the sense, what happens? The left limit and the right limit must be same. That means my x square and x must be same, so that even though it is oscillating, they can be same. Right? This function is continuous at the points where x square and x are same. When can this happen? This can happen only if x square minus x is 0. That is, x times of x minus 1 has to be 0, which means what? At the points x 0 and 1, the function is being continuous. Right? If you have to check with that limit idea, let us do it. Okay, let me check for 1. So 1 plus and 1 minus, let us do. Okay, f of x and f of x, and this is what? This is f of 1 plus h as h is 0, and this is f of 1 minus h as h is 0. Okay, so these two things has to be same. When will it happen? This will happen only if these two entries are same. So be it 1 square or simply actually this is 1 plus h square. Sorry, just a minute. Yeah, you will have two possibilities. It is either 1 plus h whole square or simply 1 plus h, and you will have to substitute h is 0 in these two cases. When you give h is 0, both this must give you the same result. Yes, it is giving me the same result. Similarly, here also what? 1 minus h whole square or simply 1 minus h, and h is going to be 0. Right? Both this gives me the same result. Hence, this exists. Right? Similarly, you may check at the point 0, that is also happen to be same. Therefore, the given function f of x is continuous at x is 0 and x is 1. Now, a natural question arose is that can we construct a function which is continuous only at a finite number of points? Till now, we have seen some examples. The first function was nowhere continuous. The second function was continuous at only 1 point, and this function is turning to be continuous at only 2 points. So, can we construct any function which is continuous at only a finite number of points? Yes, of course we can construct. Now, let us construct some function which is continuous at the points 1, 2 and 3. Okay, I need a function f of x which is continuous at only these 3 points and nowhere else. Okay, if it is so, just do x minus 1 times of x minus 2 times of x minus 3, make it equal to 0. Right? And what? Multiply it, x square minus 3x plus 2 times of x minus 3, which is 0, and this is going to be x cube minus 3x square plus 2x plus 2x minus 3x square plus 9x minus 6 is 0. This is what? X cube minus 6x square plus 11x minus 6 is 0. Among this, have only one term in one side, take everything else to the next side. Okay, that is your wish. You may take only one of the term in one side and take everything else to the next side, or you may have two terms in one side and take everything else to the next side. This is the expression. Okay, when you equate these two, actually this is a kind of two expressions. When you equate these two, this has to give you an equation, and when you solve this equation, you must be able to get only three values, and at those three values the function is turning to be continuous. Right? That is the idea. I have done it in this way. You may do it in another way as well. Now just put these things in a piecewise function, that is x cube if my x is in the set of irrationals, and 6x square minus 11x plus 6 if my x is a rational quantity. Even this is my wish. I may put this in the rational and this in the irrational. So with this, actually you have four things, right? You may have this one and take everything else to the next side. You may have these two and take this to next side. You may have these three and take this to next side. Okay, similarly you may have this and take the rest three to the next side. In this way you will have many combinations, and after forming those combinations you may put one among this in the irrationals and the other in the rationals. In this way also you may switch. Okay, so here actually I have not constructed a single function. I have given you an idea to construct many functions which are being continuous only at these 3 points. Right? Now let us get into the another problem. That is, my f of x is defined in the form of x 0 smaller than or equals x smaller than 1 and minus x if 1 0 otherwise. Okay, plainly speaking, continuous functions means the graph of the function which do not admit any break or any gap. Okay, you may see the graph of this function in the screen. Here you may see that the function is changing its behavior at 2 points. Okay, only at those 2 points the function is changing its behavior. Other than that, the function is going in a smooth way. Okay, what are those points? Those points are 0 and 1. Even in the function, you may see that it is defined piecewise. Okay, at 0 it is changing its behavior till actually this otherwise category is what? This is minus infinity to 0, right? So in this the function is being 0. Okay, the value is 0. At the point 0 the function is changing its behavior and it is defined in this way, and after that it is defined in this way. Now we will have to check the continuity at those 2 points, that is 0 and 1, and all other points. Since the behavior is not changing, we may say that the function is continuous, because in these also we do not have any denominator part. If we have some denominator part, that may give you divide by 0 or growing infinitely. These situations may arise. Here you don't have the possibility of those situations. Hence, we do not need to check about the continuity at the points where x not equals 0 and x not equals 1. Those two are the troublesome points. Let us check them. Okay. First, let us see what is this thing. At the point 0, let us do it. Okay. Of this is what? Limit h approaches 0, f of 0 plus h. So f of 0 plus h. Remember, this h is always a positive quantity. We are writing 0 plus h or 0 minus h. So h is a very small quantity which is positive. Right? So 0 plus h in the sense it is coming in this category. Hence, this is going to be limit h approaches 0 of 0 plus h, and when you give h as 0, you are going to get 0. Right? Okay, let us do here. It is what? Limit h approaches 0, f of 0 minus h. 0 minus h. It is going somewhat slight left to 0, which means it is a negative quantity. Therefore, this lands in this category, and the function value is 0 here. So what you have is limit h approaches 0 of 0, which is 0. Right? So here you may see that limit x approaches 0 of f of x, is being 0 in both the cases, therefore the limit is 0. And what is f of 0? F of 0 is defined here because 0 is included in this interval and is 0. Therefore f is continuous at 0. Okay, now we'll have to check the continuity of f at 1. Okay, let's do it. Limit x approaches 1 plus of f of x. 1 plus in the sense, I am not doing all such steps, I am just going to do it directly. 1 plus in the sense it lands in this category, therefore it is minus x. So minus of 1 plus h, and I am going to give h 0. Okay, limit h approaches 0 of minus of 1 plus h and is minus 1. Okay, and similarly limit x approaches 1 minus of f of x in the sense 1 minus means 1 minus h, therefore it is some quantity which is lesser than 1 and therefore it lands in this category and hence it is going to be 1. So what you get here is limit x approaches 1, f of x does not exist. When this limit does not exist, we say that the function is not continuous at that point. Okay, so these two are the points at which the function was changing its behavior, and we have checked for the continuity at those 2 points, and we found that 0 is a point of continuity and 1 is not a point of continuity. Hence the given function f of x is continuous in minus infinity comma 1 union 1 comma infinity. Okay, now let me give you a question. Is this f? Okay, since we have 3 things, let us name f1, f2 and f3. Okay, is f3 of x continuous in closed at minus 5 comma 1? So this is open, so no issues. This is closed. Yes, of if. Okay, actually what was the region of continuity? Okay, what are the points at which the function is being continuous in this interval? Okay, if you have any interval E which is being a subset of this interval, then of course the function is continuous in the subset. Okay, here you may see that minus 5 comma 1 is a subset of minus infinity comma 1 union 1 comma infinity. Therefore f3 is continuous in minus 5 comma 1, and this result is true in general. It is true for all the functions. Okay, if you have found the points or the sets in which the function is being continuous, on any subset of the possible set will admit all the points to be continuous for the function. Okay, thank you for watching.